Today we are dealing with horizontal problems only. Vertical ones are a little bit more challenging, but we'll get to those. So here we have an object of mass 1.5 kilograms. It's tied to the end of a string 0.5 meters long, swung in a horizontal circle with UCM. So just like you were doing a couple days ago. Such that it makes 5 revolutions in 4 seconds. Find the frequency, find the period, find the speed, find the centripetal acceleration. There's 2 different ways you can do that. And find the tension in the string. Now I haven't really taught you a whole lot about frequency, so let's just sort of make a little note here. That frequency is revolutions per second. Right? Frequency is the revolutions per second. And the unit for frequency is the hertz, just like the rental car company. I'm not really sure why they picked that name. When you go and buy a computer, back in my day it was megahertz, but of course now it's gigahertz. What they're referring to there is the processing power. It's the number of cycles, number of computing revolutions, if you want to say, per second. Okay, so the gigahertz, that when you're talking about computers, it refers to the same kind of thing. And the inverse of frequency is the period. And period is the seconds per revolution. And the unit for that is just the second. And they are inverses of each other. Okay, the period is the time for 1 revolution, and the frequency is the number of revolutions in 1 second. They are opposites of each other. Okay? And therefore frequency is 1 over period, 1 over t, and t is equal to 1 over f. They are interchangeable. Okay, so you probably should have those little formulas on a cheat sheet, and you need to be able to sort of determine frequency and period relatively easy. Oddly enough, it's usually the first step in the problem, and if you get it wrong, it can make everything else wrong. Fortunately, I know that that's a usual common mistake, and I follow through. So just be careful. So if you've got, in this case here, we've got 5 revolutions in 4 seconds, so find the frequency. Frequency is revolutions per second. So we're going to take the frequency, I guess just f, and it's going to equal 5 divided by 4, or 1.25, and the abbreviation for hertz is Hz. 1.25 hertz. There's got to be a joke in there somewhere, right? There is? Just for interest's sake, the period then would be? It's not hertz squared, Hz. Hz, it's not a 2. Hz, yeah. All right. 4 over 5 is the period, which is 0.8 seconds. Okay? And if you also went 1 over 1.25, you would get 0.8. Okay? So they're sort of flip-flops of each other. Did I tell you what you call a Frenchman wearing sandals? Philippe Philop. Eh? That just makes your day a little brighter. Oh, B was the period, right? So I guess I did B already. Didn't realize I was doing it. C, the speed. Okay, so once again, speed or velocity is distance over time, and I think we did this in our sort of formula derivation. And because it's going a whole circle, that's the circumference over the time, or 2 pi r, and the time is the period. So in circular motion, v can be 2 pi r over t. 2 times pi. I got to look up the radius here. The string is 0.5 meters long, and our time period is 0.8. 2 times pi, that's 0.5 divided by 0.8. 3.93 meters per second. So far, so good, everyone? Okay, so now the AC, centripetal acceleration. Two different ways. So the formulas that I showed you are, the one, AC was V squared over R. .93 squared, radius 0.5. Now, I always get kids asking me, I don't know why I do this. Sometimes R is little r, sometimes R is capital R. I've yet to see a rhyme or a reason for it. Okay, so they are one and the same. For whatever reason, in this formula, I tend to use big R, and in this one here, I tend to use little r. I should try to stop that. .9 meters per second squared, because it's acceleration. Now, there's another way to do it. It asks for both ways, so I just want to show you this. I don't think I would ask you this on a test, but just in case you need to see it another way, remember that it's also 4 pi squared r all over t squared. And remember, it's pi squared r, not pi r squared. 4 pi squared radius 0.5 all over t squared 0.8 squared. And what should that give you? 30.9. It appears that in my notes here I've got 30.8, but they are one and the same. It's likely just a rounding issue. Okay, so two different ways. Is that a fair amount of centripetal force? Or sorry, centripetal acceleration? Yeah, it is. That's a reasonably high number, right? It's because it's changing the direction, and it's moving 4 meters per second. That's pretty quick. Okay, so now the string tension. So as this thing is being whipped around in a circle, like so, right? There is this tension in the string that is providing the centripetal force. So the tension in the string is the centripetal force. FC. Yep. MAC. Or if you want, you could just go straight to FC is MB squared over R. Basically, that's just this one with an M in front. Or you could also go FC is equal to M4 pi squared R all over T squared. Any of those would work. But seeing as we've got these already, let's just use this one. Okay, so you can use FC is equal to MAC. You can use FC is equal to MB squared over R, or you could use FC as M4 pi squared R over T squared. Any of those will work. And they're going to give you 1.5, and we'll use the 30.9, and you get 46.2 newtons. Looking at question number 2 here, a little bit different. A string can withstand up to 7.5 kilograms hung vertically on it. Now you have to be careful. Always look for the word vertical or horizontal. But in this particular question, the string can withstand up to 7.5 kilograms hung vertically on it, but the circle itself is a horizontal circle. So what's going on here? Well, the 7.5 kilograms is the maximum tension that string can withstand. Just like when they call like a 20-pound test on a fishing line, or they give you a maximum rating on a chain or a rope, that's what this is all about here, right? So this 7.5 kilograms is the maximum tension allowed in the string, and then it's put into a horizontal circle. Okay? So step 1 is to find that maximum tension that is made up of this weight force. So it's just mass times gravity. 7.5 times minus 9.8 gives you 70 minus 73.5 newtons. That's the maximum tension that this string will withstand. And if you whip it around in a circle fast enough, what will happen? It'll break. The string will reach its maximum tensile strength and break. And of course, engineers would be something they'd be concerned about. Okay, so we are to now find the maximum speed reached before braking. So the maximum speed, or the speed that it goes when braking, is when the force is how much? That much. Okay, so we're going to go straight to Fc is equal to mv squared over r. We're going to put in our, now does it have to be negative? Is the direction important here? In fact, the direction is towards the center of the circle, right? So it's not really important, it's just going to break. So 73.5. Now, you'll notice there are two masses in the question. There's a 7.5 kilogram mass and there's a 2 kilogram mass. No? Let's read it carefully. A string can withstand up to 7.5 kilograms hung vertically on it, and then it breaks. A piece of string 4 meters long is used to whirl a 2 kilogram mass in a horizontal circle. So this is the maximum mass vertically. The actual mass in the circle is 2. So watch out for that. We're solving for v squared. Our radius is, it's a 4 meter long piece of string. It's pretty long. Can you do the math there? Okay, it's going to be 4 times 73.5. You're going to divide by 2, and that's going to equal v squared. So then you got to take the square root of it, right? And you should get I get 12.1 meters per second. I'll let you try that to make sure you can do it. All right, and the last step, the period of the motion at break time. So when it breaks, what is the time for one revolution? So we are looking for the t value when the v value is that, right? I think you should have t is equal to 2 pi r over v. I think I know why I started using the capital R's, because my lowercase r's and my v's look too much alike. I don't think I made it any better. Shane, when I sit there, am I in your way?
Yes, but then if I sit here,
Oh, okay. Well, how about I do this? Does that help? Does that help?
yes, it does.
Okay. So 2 pi, radius was 4, the velocity is 12.1. I get 2.08 seconds. That's not so bad. I'll pause again. All right. Now, normally in the old days, I used to do vertically now, but I've separated that now. So I'm kind of jumping ahead a little bit here in my mind, but you guys don't see it any difference, right? I'm going to give you, in the textbook, there's some interesting stuff. So I just want to show you this. Remember that t is equal to 1 over f and f is equal to 1 over t. I just showed you that earlier today. So that means that if you take v equals 2 pi r over t, because the 1 over t is equal to f, that means that I can replace the divide by t with a f on the top, and you get this new formula here, which you can use if you want, right? I mean, you can always take t, you can always take the frequency, flip it to get the period, and then do this, but if you want, you can do it all in one step and say that v equals 2 pi rf. And likewise, you can take a equals 4 pi squared r over t squared. The over t squared can be replaced with a f squared. That f there should be squared. So those are two sort of, I wouldn't say new, but they're combination formulas that do appear in the textbook. And the only reason I point them out is on the off chance that someone's looking for some extra help in the textbook and you're wondering what's going on. But you can always take frequency and turn it into period and then just use these two here if you want. Okay? So the last question is one from the textbook. It's somewhat amusing. A 0.20 gram flea sits at a distance of 5 centimeters from the center of a rotating LP record. Now, first of all, who weighs fleas? Do you know what a record is, folks? They are coming back, right? So, yeah, the DJs use them, right? Granny's probably got them. I remember listening to Willie Nelson at my grandma's house on record. Do you really?
They play it, cinema plays it, it doesn't work.
Doesn't work anymore?
Well, because I could use it all the time. You have to spin it myself.
Oh.
And twist it.
And you couldn't quite spin it fast enough? You had
Well,
Twisted
I
Sister?
learned how to do it the right way so I could play.
Oh, so when you did the other way, you got the backwards satanic messaging?
Yeah, it was actually bad. It was
I remember doing that as a kid too, taking records and doing them backwards to listen to the backwards satanic messages that didn't exist.
Yeah.
Yeah.
The one like.
Or now I'm sure you can just go on YouTube and hear them. They still don't exist.
Backwards.
Yeah. Does anyone know what LP stands for? It's not Louisiana Pacific. No. Long playing record. It had 5 songs on one side, sometimes 6. If it was the extended Rush version, then it might be one song completely, 12 minutes, 14-minute song on one side. So LP stands for long play. Before my time, way back when, they would only have one song on either side. So LPs came out, and they were the grooves were closer together, which meant that you could put more songs on one side. And then you had the little 45s too, which were a single one. Okay. And most LPs would rotate at 33 1/3 revolutions per second, but this particular one is rotating at 77 for some reason in the book. I think actually the old records were 78s, if I'm not mistaken. So I don't know where the textbook came up with 77. So there's some history for you. Maybe Connor can bring in his Twisted Sister album and we can look at the artwork. It's got a record player and an 8-track?
Record player on top of an 8-track.
That's pretty cool.
Cassette player and radio.
Oh, yeah?
It's really cool.
I had my uncle, who oddly enough just used to live across the street when I was a kid. He gave me his big stereo. It was the same thing. It was a big console, big wooden thing. It was longer than this table. 2 speakers. The really fancy ones had a TV in the middle, but I didn't have that. But there was a record player, and there was an FM radio. I think it had AM as well, and a cassette tape on the far right-hand side. And you could buy, did I say cassette? 8-track. You could buy little adapters. And I remember driving around with a friend of mine. He had a 77 Mustang with the 8-track player, and you had a little adapter so you could put our 80s cassettes in, this 8-track. Completely tangential to any of this stuff. Means nothing. All right. So back to our poor flea on the record here. So we've got a 0.20 gram flea sitting at a distance of 5 centimeters from the center of a rotating LP record. The record rotates at 77 RPM. What centripetal force must be provided by friction to cause the flea to maintain his UCM? In other words, here's the record, right? Here's the little flea. As it's rotating around, what is he trying to do? He's trying to hold on, exactly. Inertia is causing him to want to fly off. What's holding him in place? Friction. Okay? Friction is there. So in other words, the friction force is the centripetal force. The friction force is the centripetal force. Now, what units what quantities do we have? We have mass. We have, now the distance is 5 centimeters. Did you note that this is in grams? So what do we have to do actually? Convert it to kilograms. So divide by 1,000. So 0.0002 divided by 1,000. The radius, the distance is 5 centimeters. That's got to be in meters, 0.05. And the record is rotating at 77 RPM. Did I tell you what RPM stood for? Revolutions or rotations, same thing, per minute. So it's 77 per minute or 77 times around every 60 seconds. We care about it being in seconds. Okay, so the first step is going to be to convert that one. So 77 revolutions in 60 seconds divided by 60 is going to give us 1.28 revolutions in 1 second, which is in hertz, and that is known as the frequency. Okay? And this value of f here, now note, this is little f, frequency, this is big F force, right? Two different things. Okay, so we can use our new friend that I just showed you. We can now go to Fc is equal to m4 pi squared f. Is it f or f squared? F squared. I always forget. These are the ones I always get mixed up with. I think this is the way the book does it. So our mass is 0.0002 times 4 pi squared, which remember from yesterday was our K value that we came up with. 4 pi squared, 4 pi squared, and the frequency is 1.28 squared. And so you get a centripetal force of 0.00, it's a flea, it's going to be tiny, 0.0065 newtons. I'm glad to see you're checking my work. I'm going to assume that I got it right. It's been right for a few years on this piece of paper, so. Now, it's not in the book, and it's not on your question, but you got lots of room on your page, right? So I'm going to give you a preview of what's to come in the future. I'm going to say to you, what mu value do I need for this to work? Here's a bit of a throwback Tuesday. What mu value do I need to work? Well, remember, mu equals FF over Fn. Do I have FF? I do. I have this number here. That's my FF. Do I have Fn? I don't, but Fn is simply the FW, mass times gravity. Make sure it's in kilograms, 0.0002 times 9.8. And now I'm going to need a calculator because I never finished this part. Hi, Pauline.
Are you sure your S?
Am I sure? Well, I'm going with this. Did I mess up? You got it?
I'm going 0.013.
Did you do pi squared? Did you do 1.28 squared? Did I forget to put the letter R in the formula?
Yes, you did.
I did, didn't I?
Yes.
It's m4 pi squared R. You'd think so, but he really loves the C. And no, we didn't plan that this morning.
It's really
Thank you, ladies. So there's got to be a 0.05 in there, and when you do that, you should get the right answer, I think. The R is not squared. Does that work now, Bailey?
Yes.
Okay, thank you. Thank you for spotting my mistake. All right, so now we got to take this value here. We got to find this FW value. 0.0002 times 9.8. That's going to be 0.00196. And that's going over to here. So the minimum mu value is going to be my FF, 0.00065, divided by my FN, 0.00196, and you get 0. I get 0.33. Does that seem like a reasonable mu value? Remember, mu values are going to always be less than 1, or 99% of the time less than 1. Wood on wood, I think that you found was about 0.25 or 0.3. So that seems pretty reasonable. Right? Yes. Oh, I'm just saying that on here because I know Josh will be watching.
Think you'll actually do that?